Everyone, class 33, we're looking at inclined planes. There's a lot to do here, so let's get going. So the first thing you had to do was just make some predictions for numbers 1, 2, and 3. A block sitting on a flat, frictionless surface. What is the acceleration of the block? Obviously, it's just sitting there. The acceleration is going to be 0 meters per second squared. The next one, let's say you have a block and it's against a vertical wall. So here's my block, here's my vertical wall. What would be the acceleration as you let go of it? Hopefully you realize it's going to accelerate at 9.8 meters per second squared. Those are both actually right. We're going to prove it mathematically later. This one's a little bit more challenging. What if the inclined plane were at an angle of 45 degrees? Okay, what would the acceleration be in that case? Many of you took guesses. I don't know. 4.9 meters per second, maybe meters per second squared, maybe. That's actually not the right answer, but that was a really common one that people picked. So let's check it out. Okay, so I'm actually going to put an X through that so there's no confusion. That's not the answer. All right, so the first thing we did was we drew the forces acting on this block on a frictionless inclined plane. So the first force was the normal force because, anytime you're touching a surface, there's a normal force and it is perpendicular to the surface. So that's the normal force. The other force is the force of gravity. Now, many people weren't really sure which way it pointed. Remember, gravity points down. So the force of gravity is going to go down. Now, I'm going to actually refer to this as mg. Okay, that's the same as fg, right, on near Earth's surface. So that should be fine to do. Now, we're not quite done yet because it's a little bit challenging to figure out, what the forces are that are pulling this object down the incline. Like, what's the normal force's value? Because if someone asked you, well, why does it go down the incline? They would say gravity, and they'd be right that the force of gravity is what pulls it down the incline. But it's not the whole force of gravity that pulls it down the incline. Think about it this way. If I'm on a hill and let's say I'm pulling somebody up a hill with a sled, okay? I don't have to pull up their whole weight, right? It's a little bit easier. I'm only pulling up a portion of their weight and actually a component of their weight. So we have to actually break this up into x and y components like we've done before, but instead of x and y, we're actually going to do parallel to the inclined plane. Okay, we're going to call this parallel, and perpendicular to the inclined plane. You could think about these like x and y and realize that they're still perpendicular to each other, just like x and y are perpendicular to each other. Perpendicular. So perpendicular is perpendicular to the inclined plane, parallel is parallel to the inclined plane. Now, for reasons that we don't really need to get into, but you could try to prove it to yourself, this angle here of the incline is congruent to and equal to this angle here, okay? Now we need to break up mg into x and y components, or specifically horizontal and vertical components. Excuse me, perpendicular and parallel components. So let's do that right now. So we're going to make it into a triangle. We have our perpendicular component, and we have our parallel component. These make a nice right triangle. Now, I don't like to draw the parallel component down here, but we'll leave it for now. That parallel component in red is the opposite, so that is going to be mg sine theta. And the perpendicular component is going to be the adjacent side, so that's mg cosine theta. Now, it can be a little bit confusing, this mg sine theta, because it's far away from the middle of the box, so I'm just going to move that. So I'm going to get rid of mg sine theta there, and I'm going to draw it right here. mg sine theta, all right? So there are only two forces acting on this box, normal force and the force of gravity, mg. But mg, just for mathematical reasons, we have to break it up into components. Those components are mg sine theta, that points down the incline, and mg cosine theta, that points perpendicular to the incline. So the component of the weight parallel to the incline is mg sine theta. And just remember that by saying mg, well, that's weight, but sine, well, how do you know sine or cosine? Sine makes you slide, the one that makes you slide down the inclined plane. And the component perpendicular to the incline is mg cosine theta. Cos keeps you close, it points towards the surface of the inclined plane. It's honestly, just memorize these. I hate saying it, just memorize these. All right? So let's say you have a block with a mass of 6 kilograms on an incline of 30 degrees. What is the weight of the block? That's simply mg. This is mg. So this is going to be 6 kilograms times 9.8 meters per second squared, and you get 58 newtons. Let me fix that, put newtons on there. All right, the component of the weight parallel, that's mg sine theta. All right, so that's going to be 6 times 9.8 sine of 30. That's 29.4. Perpendicular is mg cosine theta. So that's going to be 6 times 9.8 times cosine of 30, and you get about 51. Make sure your calculator's in degrees mode. All right, let's check out this next part. What is the normal force acting on the block? Hint, do A equals F net over M in the perpendicular direction. So just like X and Y, we can only do our net force equation in either the X direction or the Y direction at any given time. You can't do both together. Same with perpendicular and parallel, you can only do one at a time. So we're going to start with the perpendicular forces. All right, perpendicular forces. So our two perpendicular forces are normal force and mg cosine theta. So I have A perpendicular equals F net perpendicular over mass. Now the acceleration perpendicular, well, let's think. Is it accelerating at all in this direction away from or into the incline? No. So A perpendicular is going to be 0. F net perpendicular are the two forces in the perpendicular direction, which are normal force, and negative mg, because you got to make one of them negative, cosine theta, all over the mass. Multiply both sides by mass. Therefore, you get 0 equals normal force minus mg cosine theta. Where'd the mass go? Again, you multiply both sides by mass. 0 times mass is 0. So I get that the normal force is equal to mg cosine theta. Wait, that's the same as the perpendicular component. Yeah, so it's actually the same thing. It's 51 newtons. So that's why the perpendicular component is important. The parallel component is important for figuring out how fast we go down the inclined plane. So what is the only force pulling it down the inclined plane? Well, why don't we look at our picture? The only thing pointing down the inclined plane, well, mg is really the force, but the reason I put force in quotes is because specifically mg sine theta is what pulls it down the inclined plane. So this is mg sine theta. All right, so if we do the parallel direction, we have A parallel equals F net parallel over mass. A parallel is what you're looking for. That's not 0 because it's definitely accelerating down the incline, or we can prove whether it is or isn't. The only force in the parallel direction is mg sine theta over m. Masses cancel, and I get g sine theta. So the acceleration down the incline is given by g sine theta. So does the mass of the block matter? No. Why not? It cancels out. Basically, the reason it cancels out and the reason it doesn't matter is because the more mass you have, the more weight that pulls you down the incline, the greater the force of gravity pulling you down the incline is. But more mass makes the denominator here bigger. It requires more force to accelerate you. Those two cancel out. Therefore, our acceleration is g sine theta. Okay, so it doesn't matter how heavy you are. If you go on a sled and your friend goes on a sled and you have different masses, you will accelerate down the inclined plane or down this hill with the exact same acceleration, equal to g sine theta. So it's kind of makes sense though, like, if you have an object in free fall, its acceleration is g. If it's on a hill, it's g times sine theta. Again, because sine makes you slide. That's how you know it's sine, not cosine. All right, so a block sitting on a flat frictionless surface, let's try it out. G sine theta, right? That's what we're gonna use for all of these. So let's see, 9.8 times sine of 0 degrees. That's 0 meters per second squared. Let's try against a frictionless surface, or against a wall rather. 9.8 sine of 90. Sine of 90 is 1. Hopefully you know that. So you end up getting 9.8 meters per second squared. These are what we predicted, but now we're proving it mathematically that that is the acceleration. So at an angle of 45 degrees, a lot of people thought that it would be 4.9 meters per second squared. Let's see. Sine of 45 degrees. Again, you have to be in degrees mode. This actually comes out to be 6.9 meters per second squared. All right, and the last one, I give you the acceleration, I ask you to find the angle. So the A equals G sine theta, right? So A equals G sine theta. So A is going to be 4.9, G is going to be 9.8 sine theta. Sorry, I'm gonna give you a lot of room here. Divide both sides by 9.8, you get 0.5 equals sine theta. Therefore, the inverse sine of 0.5 equals theta, which equals 30 degrees. All right, now these two are Regents questions. You must know how to do these too, okay? The biggest place people struggled with these is that they didn't quite understand what was asked of them and what the givens were. Be careful for this one. It says you have a 1.0 times 10 to the 5 Newton truck. That is not the mass, okay? That is actually mg. Mg, that's the weight, is 1 times 10 to the 5. And theta is 8 degrees. Over here, the weight of the box, mg, is 46 newtons. The dead giveaway is the unit. If it was in kilograms, yeah, it would be the mass, but it's not in this case. Theta is 25 degrees. Here in number 5, it's asking for the parallel component of the weight. This one's asking for the parallel component of the weight. So this isn't g sine theta over here on the left. This is actually going to be mg sine theta. So mg is 1 times 10 to the 5 times sine of 8 degrees, and you get 1.4 times 10 to the 4 newtons. Over here, perpendicular is cosine theta. So we have 46 times cosine of 25, and we get about 42 newtons. All right, that's how you do it. We'll have more practice with this, but just make sure you're able to do these two questions for sure without any issues. If you can do these two, you're good for this topic. All right, have a wonderful day, and we'll see you soon.